Okay, welcome back, everyone. So, we are now talking about nomenclature. Um, First, let's talk about ionic compounds. So, um, ionic compounds, they are composed of elements forming ions. So usually when we say ions, they are formed from metals and nonmetals, from a metal and nonmetal. So it's important that we can distinguish between what a metal and a nonmetal is. Okay, so metals are usually on the left side of the periodic table. Nonmetals are on the right side of the periodic table. So when we have ions, we can classify them as cation or anions. So a cation, you will lose electrons to form positively charged ions. And anions are the exact opposite. You gain electrons to form negatively charged ions. So a cation is positively charged because if you lose an electron, that means the number of protons you had in the atom is now greater than the number of electrons. That's why there's an overabundance or abundance of positive charge. So you end up with a positive charge. The number in front of the charge depends on how many electrons you lost. Anions, you gain more electrons, so now more negative charge is present, and so the value of the negative charge or the number in front of it will depend on how many electrons you gain. So let's go over some examples here. So first we have this sodium atom. So we know the sodium atom has one valence electron. It's in group 1 of the periodic table. So we have let's put one electron on sodium. Then bromine is in group 7 of the periodic table. And so group 7 means you have 7 valence electrons. So we're going to write 7 electrons around bromine. Okay. So what happens here is these atoms will react where sodium will donate its electron to bromine, and now it will form a pair of ions. So that's an ionic compound. Sodium has lost an electron, so we say it's positive 1. Bromine now has 8 valence electrons around it, and now it becomes negative 1 charge. And when this happens, this interaction of positive and negative charge becomes an ionic bond. So an ionic bond forms between sodium and bromine. Ionic bond okay? So now we have a ionic bond between sodium and bromine. So this is what we call electrostatic attraction, or the attraction between oppositely charged ions. All right, now let's do an example where we have more than one valence electron on the metal. So metal, in this case, is magnesium, Mg. So magnesium has 2 valence electrons. And chlorine, like bromine, has 7 valence electrons. Okay. So in this case, so here, magnesium can donate 2 valence electrons. So one to this chlorine atom, this one to this chlorine atom. So now we get Cl minus on one side, magnesium 2 plus because it has lost 2 electrons, and then chlorine, the other chloride ion on the left here. Okay, so now we have the magnesium chloride compound, MgCl2, and this one on the right, and the one above it is NaBr. So Na, like nah bro. So NaBr. Right there. Okay? So this is example of ionic bonds. So sodium is in group 1 on the, so let's fill out this vocabulary here to kind of summarize what we just went over. So it's in group 1 on a periodic table. So it likes to lose 1 electron to obtain a noble gas configuration, or what we call an octet of electrons. So just think of an octet as a chemical electron configuration for an atom that an atom likes to obtain when it participates in chemical reactions. It participates in chemical reactions because it wants to attain this valence shell where there's 8 electrons in the outermost shell of the atom. That's a particularly stable state for atoms, and they participate in reactions to obtain this kind of configuration. So this cation is called D. So for cations, we just label the name of the atom and just write ion at the end for cations. So this is the sodium ion. Okay. Chlorine is in group 7 on the periodic table, so let's write 7 there. And so it likes to gain electrons, or it likes to gain 1 electron. Oops, sorry, I kind of erased it. Gain 1 electron to obtain a noble gas configuration. So we call this anion the chloride anion. So since this compound is chemically different, or is different from a chlorine atom, we need to change the naming of this so we can differentiate it. So we call it the chloride ion, as opposed from chlorine atom, which is not negatively charged and doesn't have 8 electrons. Okay. So the other element we have to describe is magnesium. It's in group 2 on the periodic table, and it likes, like sodium, it's a metal and likes to lose 2 electrons. So we can classify this. Sodium is a metal, so metal here, metal, non-metal, metal. So it loses 2 electrons to gain a noble gas configuration. So this cation is called the magnesium ion. Okay, so that's ionic compounds. Now let's go over molecular compounds. What are molecular compounds? So molecular compounds are, they're compounds, so they are compounds that are made up of up of elements that share electrons. So the elements here are two nonmetal elements. So two nonmetal elements. So in ionic, you have a metal and a nonmetal. In molecular compounds, you have two nonmetal elements. Okay, so they don't form ions. So one good example of this is water. So water is made from hydrogen and oxygen atoms. But to depict how covalent bonding works, we're going to you look at this very simplistic example where we're reacting two hydrogen atoms and oxygen atoms. So we're not working with H2 or O2 molecule, just H atom, O atom. So we know hydrogen's in group 1, so it has one valence electron here. Oxygen has 6 valence electrons because it's in group 6. So when we're drawing these Lewis dot structures, we just want to make sure that each unpaired electron is occupying a different orbital. So you wouldn't want to like pair those two unpaired electrons and have one empty orbital. That would be unstable. So this is how we should draw it. And then we're going to show how covalent bonding works. You're going to share electrons. So each atom is going to donate a lone pair. And we use these half hook arrows or fish hook arrows to represent that one electron is moving to form a bond. Like so. And then we get the formation of two single bonds to oxygen now. And see here that the lone pairs on the oxygen atom that I just drew are not changing. So they remain unchanged and are not involved in the chemical reaction. So these are called lone pairs of electrons. So lone pair of electrons. So lone pair electrons either like to exist as lone pairs or as chemical bonds. So sometimes you may see electrons that are not paired. We call those radical species. They're typically reactive, but there are some stable radicals that can be isolated and you can see them in their physical form, but they are rare. So most of the time, molecules have no unpaired electrons, and all the electrons are either in the form of chemical bonds or lone pairs of electrons on an atom. Okay. So, in molecular compounds, the chemical bonds that are formed between elements are covalent. They are not ionic. So covalent means just like when you co-sign a loan or a lease, you're kind of sharing that burden, or sharing that responsibility. So in this case, covalent, you're sharing electrons to share a chemical bond. Okay, where electrons are shared. So this molecule is called water, but chemically speaking, we can call it by its formal name, which is dihydrogen monoxide. Like that. Okay? So now that we have described bonding for both types, let's talk about naming each type. So to name ionic compounds, we take the name of the cation and the ion, and we simply pair them together. So if we go back up here, we had sodium ion. So sodium ion here. So just look right here, sodium sodium ion, and then for chloride, for the chlorine ion, we had chloride ion right there. So we combine those two names, but we remove ions, because when we name ionic compounds, they're no longer ions because they come together to form a compound which is neutral. So we take both of those names and remove ion from those names and bring them together, and we get sodium chloride. For MgCl2, we had if we go back up here, magnesium, and then chloride ion again. So since there's two chlorine ions in the formula, we actually don't have to do anything to the name. We just combine the names again like we did for sodium chloride. So we get magnesium chloride. Okay. So even though there's two chlorides, we don't call it magnesium dichloride. That wouldn't be appropriate because there's only one formula that is known as magnesium chloride, and that's MgCl2. So magnesium only exists in the 2+ state. There's no compound we have found that seems to suggest that it wouldn't be 2+. So it's very straightforward for elements in groups 1, 2, and 3. We start getting things start getting a little bit more complicated when you talk about the transition metals, which is that large group in the middle of the periodic table that separates the metals from the nonmetals. All right, barium, BAL, barium oxide. So if we think about it, Ba is 2+. So in this compound, barium has a charge of 2+. Because it's like magnesium, so it'll have a 2+ charge. So everything in group 2 has 2+. Barium's in the periodic table in group 2, so that's why it has 2+. Oxygen is in group 6, and it likes to gain 2 electrons to get a octet. Because oxygen has 6 electrons, so it needs 2 to gain an octet. So it commonly forms 2- ions, so 2-. So we call this barium oxide. Okay, so this has a typo. This should be GAN, GAN. So gallium is in group 3. It's a metal, so it usually has a charge of Ga3+. So you can also use the group number to know what charge it'll most likely form. So gallium is in group 3, metal, 3+. Sodium, group 1, metal, +1. Magnesium, barium, group 2, metal, 2+. Nitrogen is not a metal, it's a non-metal, and it's group 5. So you can't use the same analogy for the non-metals. So for example, oxygen group 6, but you can't say, oh, it's 6-. That would be if it was a metal. It's a non-metal, so it wants to achieve an octet. So you would have to subtract 6 from 8 to figure out how many electrons it needs to get an octet, and that number will give you the charge it will have when it combines in ionic compounds. So oxygen, 6 from 8 is 2, so it'll be 2-. Nitrogen's in group 5, 5 from 8 is 3, so nitrogen is 3-. And you see here, for both of these last two examples, we didn't need to put subscripts. Or sorry, I'm going backwards. We're not actually translating yet. Sorry about that. I mean, since we have the same charge here, even though they're the same charge, it doesn't matter. It's like sodium chloride, right? Having the charge on ionic compounds, when you're translating from a chemical formula to a name, the identity of the charge, or the number in front of the charge, doesn't influence the name at all. So we have gallium nitride. Okay, so that's gallium nitride. All right. Okay, so let's go over this last example. Then we'll use the lot in the next video. We'll finish the rest of this lecture, rest of the nomenclature. Okay, so for atoms in the central block of the periodic table, these are also called metals. They have properties of metals, but they're called transition metals because they can adopt more than one charge in their compounds. So it's not always straightforward. Okay, so we have copper chloride, and then copper, it looks like copper chloride again. So are both of these molecules copper chloride? No. So in this case, we have to look at the anion charge to determine the name for the metal. So for here example, Cl minus, all right, but we only have one Cl minus and one copper. So that means copper, for the compound to remain neutral, it must be +1. So copper must be +1. So we would call this copper parentheses 1. We had to put this in parentheses to indicate that the charge on copper is +1. And then we call this copper 1 chloride. So here the subscripts have no meaning in the name. You just identify it as the identity of the anion, so chloride. So in the second example, we have copper chloride, but we have two of them. So we have two chlorides, right? That would give us a charge of 2 minus. So for copper to remain, so for copper to neutralize or make this compound neutral, copper must be 2+ to cancel out the 2 minus. Okay, so copper here is what we call copper 2 chloride. So most of the transition metals do this. Some exceptions are zinc and silver. So some exceptions, we have zinc, which is always 2+. So zinc is always 2+, and then silver is always Ag+ in its compounds. So silver plus zinc 2+. Those are the only two exceptions you'll have to know. Okay, so let's end this video here, and in the next one we'll wrap up nomenclature now between converting from chemical name to formula, and then we'll go over molecular compounds, how to write their chemical formulas based on their name and vice versa in the next video. And that'll be the last of the videos for lecture 1. All right, see you then.